All right.
So welcome to another wonderful episode of New York City Category Theory Seminar. Tonight we have Ray Puzio giving us second part of synthetic differential geometry. Take it away.
Right, so first I'd like to say is just start with the sources for this talk. So these are two things by Anders Koch. So Anders Koch is a source for synthetic differential geometry. I mean, pretty much he, Laverne, a few other people invented the subject. And in particular, I'm going by two of his things here. I have pages for them copied out that I'll be looking from. So one, there's a nice little expository paper he wrote that's called New Methods for Old Spaces. So it's an expository paper. I think it's like about 20 pages long. Introduction to the subject. Then there's a book. He's written more than one book on it, but the one that specifically I was going to refer to is called Synthetic Geometry of Manifolds. And in fact, I should mention that inside that book, so in my talk, I'm going to talk a little about Lie. In a few minutes, I'm going to get to some material on doing Lie groups in synthetic geometry, and that turns out to be in chapter 6 of his book. And in fact, I'm going to for the stuff I'm going to do in a talk, it's actually going to be section 1 of that, and I think it's some like pages 207, which I just printed out, and so that will be, where I'm getting most of that material from. But before I get to that material, I first wanted to, put a little refresher on what is synthetic differential geometry. I've done it once, and now but I'm not going to assume anyone remember, including myself, remembers very much from the last time. So I'm going to start again. But for those who do remember, I'm going to use a slightly different approach. So I'm not going to just repeat not just going to repeat the talk I gave already. So this time I decided to start introducing the subject by, well, starting with the name. So what do we mean by synthetic differential geometry? So, well, first let's start with geometry. We kind of know what geometry is. Literally, it means measuring the Earth. And of course, nowadays we use it to mean something like you're studying, some, let's say, some quantitative properties of spaces. Where spaces, well, it might be lines or planes or curves or whatever they are. All right. Now, what about the other two words, synthetic and differential? Well, synthetic, that part of a pair. So there's sort of, so how are you going to study your spaces? There's sort of two approaches. One's called synthetic, one called synthetic. Well, that's the approach where you say, well, to study my spaces, what I'm going to do is I'm going to take some operations on them, such as, for example, given 2 points, I can connect those points by a line. Given 2 lines or curves, I can take their intersection, etc. So I have I could draw perpendiculars, whatever. So I have these operations, and then in synthetic geometry, what do? We say, well, by repeatedly doing these operations, we make geometric constructions, and then we can use our geometric constructions to prove, to prove theorems, to solve problems, etc. Now, analytic approach is a different approach where you say, well, instead what we're going to do is we're going to look at numerical quantities associated to our spaces, different lengths, areas, angles, whatever, and instead of actually doing constructions with the spaces, we're just going to do some algebraic operations with these quantities. All right, so now those are two kinds, and now finally, what about differential? Well, going back to what I said about the analytic approach, we have different quantities that we're going to be studying. Distances, coordinates, whatever. So what can we do with those things? Well, one thing is we can do algebraic operations with them. Oh, so I should say differential, just like synthetic comes with analytic, this sort of comes as part of a pair. So first thing is, given those different quantities I have, I can, do algebraic operations with them. And that's usually what we call algebraic geometry. But I could also, do differential operations with them. Take derivatives, solve differential equations, and that basically gives me differential geometry. So you'd say, so you could say analytic differential geometry means I'm, basically using calculus to study my geometric spaces. So now what would we mean by synthetic differential geometry? Well, synthetic is supposed to be about doing constructions. So somehow we want to have some constructions that, somehow relate to what we would be doing with our derivatives. And the intuitive idea of how to do that actually long predates calculus, because even in the Middle Ages, you know, some geometers were thinking, well, I could, in my geometry, I could introduce infinitesimal elements and somehow, at least informally, manipulate those to obtain results. So an example might be, let's say I have a curve. I might say, well, I want to construct a tangent at this point. So what do? I can pick a point that's infinitesimally close to that, whatever that means. And then I make a construction where I connect the point to the infinitesimally close point by a line. And then there are other things that one can do, like, for example, if I want to compute say the area of this thing, I'm not going to try to draw it now, but, well, you know, there were things like, some people did say, well, imagine I somehow split it into to an infinite number of infinitesimal pieces, and maybe I can rearrange them and get some other shape whose area I know, and so on. So the idea was, you know, that at least informally, you can imagine doing synthetic geometry where I have some kind of infinitesimal spaces or infinitesimal parts of my spaces that I'm doing my constructions on. Now what we want to do here is to say, okay, that's, you know, informally I can do it, but can I make that formal? Can I actually make it formal and make good logical sense out of doing constructions with infinitesimals? All right? And that's what basically the topic of synthetic differential geometries, because even though people, you know, hundreds of years ago were doing these informal things, it was really not until maybe 50 years ago that anyone could finally find a way of making it logically precise, the same way you could make ordinary geometry precise. So to do that, let me just say a few words about how you would, how you make geometry precise or axiomatic. Of course, the idea of axioms with synthetic differential geometry goes back a long time. I remember, I think it was last week, we after all had someone talking about, Euclid and Proclus and their axioms. Now, back then, the axioms are written in natural language. In the case of Euclid and Proclus, that happened to be Greek. But we're going to use a different language. We're going to use category theory for writing down our axioms. So how do I do synthetic geometry in general using category theory? All right, well, the idea is, and by the way, slow me down if I'm going too fast. Okay, all right, so the idea is that I first need a category, obviously. So let's say I make a category. And the objects of this are going to be the spaces that I'm working with. So for example, if we were doing Euclidean geometry, they would include things like points, lines, planes, circles, and whatever other spaces you'd encounter there. And the morphisms are going to obviously be some maps between these spaces. And what types of spaces depend on what type of geometry I'm doing. So for example, if I'm doing Euclidean geometry, I want my morphisms to be maps which preserve the Euclidean distance. All right, so maps, that somehow preserve whatever relevant structure is. And now, using this, I can, do my Euclidean geometry. So for example, simple example might be, let's say I start, with a plane in Euclidean geometry. All right, so there's my plane R2. Now I might say, well, in this plane I have a point here. Right, so I could say that by saying, well, I'm going to have a map that just maps my standard point into that. Oh, and I might even have a line in there as well. All right? So my line is going to be, well, again, given, let's just call it point P, line L is that. Now, as I drew in the figure, the point lies on the line. So what does that mean? Well, that means I have a mapping from the standard point to the line that makes this diagram commute. Now, and then I can, do a little more, like for example, suppose I had, write it again, suppose I had 2 points. times 2 points. Then if you remember, what did Euclid's first axiom say? Given 2 points, there's a unique line that connects the two. And so what does that mean in category language? Well, it means that there's going to be a unique map from the line that makes this diagram commute. So you can basically take anything you would, state, take all your synthetic geometry and write it in terms of, I take a category like this one. So if I want Euclidean geometry, I have the category where, I have my Euclidean transform, the distance-preserving transform with morphisms, and do category theory with diagrams in there. Now, I can then get different kinds of geometries by switching out my category. So a simple example might be so-called, let's say, and there are many types, but just to mention one, affine geometry. And what that means, I'm going to have basically the same objects, but I'm going to have more morphisms. So instead of my morphisms being things which have to preserve Euclidean distance, they're just going to be, what do you call it? Inhomogeneous linear transforms. So a morphism is just going to be something of the form ax plus b, let's say, all right, this transform on a vector, raise a matrix beats that, so I could do that. And then there's all kinds of different geometries. So basically I can do my synthetic geometry using category. So then the game will be to figure out, okay, now how can I fit infinitesimals into this? So basically I'm going to want to do is, and I'll say in a minute how to do it, is basic idea is, well, I'm going to want to have, in addition to the ordinary spaces, I have my lines, circles, planes, etc. I'm going to want to have infinitesimal things, like an infinitesimally short line segment or something that I want to add to my category. And all right, so to see how to do that, I'm just going to go back to the algebraic side of things and just say a few words how we formalize that using category theory.
Ray, yeah. Is it that it's closed under limits and co-limits, or?
I'm going to put, so later I'm going to put axioms saying when that's the case.
Is that the synthetic part?
Well, the synthetic, it's some category. Typically, they will be closed under such things. Okay. But again, what they are depends which geometry you have. I'm just saying, if you're doing affine geometry or so, yeah, they will. The category I have there, I think, will certainly have plenty of limits and co-limits in it. But for synthetic differential geometry, in fact, I'm going to give a bunch of axioms in a minute, which actually are going to require limits. But give me 5 minutes to get to that point where I do that. So, well, I'd like to use that for more interesting things in the intro. I want to get past the introduction and by the time the talk ends. So, yes, right. So, all right. So then, like I said. And if we look at the analytic approach, well, instead of spaces and operations with them, I'm looking at doing algebraic operations on quantities. So what I can do is to say, so I think of quantities such as, areas, lengths, whatever they are, and the point is, well, I can do algebraic operations on them, so basically, that amounts to saying that given a space I can associate a ring of functions to it. So I have some field, classically it would be the real numbers. This is the number system in which my quantities take values. So classically it would be real numbers, but nowadays we consider other things like, for example, it could be a number field, could be all sorts of things. But whatever it is, I say I have an algebra over that of functions on my space. All right, so analytic with category. So for a space, so we have let's say a ring or a field. Of numbers, that's where what the things will take our values in. So like I said, classically and infinitesimal. So this talk, it'll be just real numbers, but it could be something else. And I have to say that given who's in the audience. And then, so given for each space, I can associate to it the ring of functions on that space. Or let's ring algebra of functions, because it's an algebra over that field. Or ring based thing of and then to a mapping between spaces, so it's called an A. So if I have two spaces, then what I'm going to get is, given a map, let's say, all right, so given two spaces, if I have, let's say, say this is the algebra of functions over space number 1, and the algebra of functions over space 2. So if I have a mapping from 1 to 2, that's going to give me a mapping from functions on 2 to functions on 1, because if I have a function on it, well, and I have a map, what do? I compose with that. I take a function here, a function there. All right, so, and in particular, this is now going to be, you know, going to be a morphism of algebras. It's going to preserve the algebraic operations of addition and multiplication, as well as the scalar multiplication by my numbers. All right. So that's how I can describe, that's a modern way of doing analytic geometry. I just say I have a category of rings with some morphisms between them. And just to tie to an example, so let's say if I wanted to do my Euclidean geometry, for example, I could, you know, describe my line or plane by something like polynomials over it. And then I wouldn't want all mappings between polynomial rings. I'd want the ones that correspond to my distance preserving functions. So I'd have a certain class of them. And the point is that, so in that way, we can say if we have a geometry I gave you synthetically by saying I have some spaces and some, you know, by giving some category of spaces and maps between them, I can I can model it analytically by saying, oh, I found some category of rings and morphisms of rings that happens to be, well, that happens to be, you know, okay, corresponds to it, but in the opposite way. Because whenever I have a mapping between spaces in one direction, I get a mapping in the other direction. Now, then what happens is you can ask, okay, what types of actual rings tend to, if I take geometries we know well, like Euclidean geometry, affine geometry, you ask, well, what type of rings do I get here? And it turns out for those classical ones, I get a very special kind of ring, rings that have no nilpotent elements. All right, so for we all get rings. The rings turn out to have no nilpotent elements. But now, once, you know, people recognize this, that you could, namely recognize that I could, you know, formulate my geometry, whether it's synthetic or analytic, in terms of category theory, and that these two correspond to each other, then natural question came up, well, why have this restriction on the rings? Why not study, you know, allow more general rings? And then basically, you know, the idea was to say, well, say given an arbitrary ring, let's just posit there's some kind of space that corresponds to it, which gets called the scheme of the space. All right, so the question is, if we buy that, what type of, you know, what have we gained? What kind of new spaces do we get? Well, let's take this. So the old ones were ones with no nilpotent elements. So let's take an algebra that has a nilpotent element in it. And here's the simplest example. I could just take, for example, things of, well, something like this. So I'm just going to take my real numbers, I'm going to add one generator, and I'm going to put one relation, which is just to put that to 0. I mean, put the square of it to 0. All right? So that's clearly nilpotent. I multiply it by itself, I get 0. And now how can I interpret this? Well, I can interpret this as real numbers where this thing that squares to 0, I can think of as an infinitesimal quantity. It's so small that when I square it, I get 0. So that means that, once we lift this restriction on, on the rings not having nilpotent elements, the things we were excluding were the infinitesimals. So if we wanted to do some kind of synthetic differential geometry, well, that means, one approach to it is let's allow these things, these nilpotent elements in. So I have these. So I say that, okay, corresponding to these rings, I'm going to get spaces. Now, furthermore, here's something I will just mention that I did last time in detail. Now I will just mention the fact. So, as I said, if we have, a mapping of, so first of all, when I talk about, functions on a space, obviously if I have a point, the functions on that space are just a copy of the field. So a single point was a function at that point, it's just a numerical value at that point. So, given a map from my algebra to the field would correspond to just, specifying a point, which means given a function on it, I specify the value of the function at that point. All right? So now I can ask, well, what happens if I take my algebra and instead I map it to this thing? Oh, and by the way, I'm going to give this here, the real numbers where I've adjoined this one thing that squares to 0, I'm just called D. Sometimes that goes under the name of dual number. All right, so I'm going to ask, well, what happens if I take some algebra and I map it to D? And you can, let's say, so let's just take a concrete instance. For example, maybe it's polynomials in one variable. And I ask, what happens, what does a mapping to that mean? It turns out to be the mapping that sends some polynomial here, f, into value of f at a point plus this square zero, the thing that squares to 0 times the derivative of it at that point. Now, furthermore, so that's for polynomial, for a ring of polynomials, and you can just, this you can just check, and just write down what it means to map, a homomorphism as a polynomial into an element of this, and you'll see that's what it works out to. But the more interesting fact is that actually and this is what makes synthetic differential geometry a thing, is that if I use not just, suppose instead of the ring of, well, if I do ordinary differential geometry, I don't just want to work with polynomials. I want to work with, transcendental functions, smooth things, because I might, for example, solve a differential equation. When I solve a differential equation, I usually don't get a polynomial or an algebraic function. I might get exponentials, sines, Bessel functions, and all kinds of non-polynomial things. So you'd say, well, the ring I want there is not just the polynomials. I'd want all smooth functions, or at least analytic ones. So the amazing fact is that if I actually take a homomorphism from the ring of, say, smooth functions to these dual numbers, they all have this form too, where I evaluate at a point in this. And I went through the reasons for my last talk. It basically amounts to the fact that I have a Taylor series. So given any smooth function, I can write it as, or let's say this way, x plus y. So if I'm expanding about x, I get, plus a remainder, and there's many forms of the remainder, but the important fact of the remainder is it's going to have a y squared times some function of x and y. And like I said, if you look at analysis books, they'll give you lots of different formulas for the remainder. But the important thing is that, well, if I go, let's say the first order, then the remainder is going to be second order. If I go to nth order, the remainder is n plus first order.
What's that notation you're using? C infinity adjoined x?
Oh, C infinity, I mean of, well, let's just do it this way. It's a funny thing. I guess that would be the more standard notation. Sorry, I was following that, but yeah, let me write it the usual way, yes. To see infinity of a line, yep.
As you know, this formalism is not unique.
What isn't, well, who, I mean, well, I'm just saying given a, yeah, that's not unique, I'm saying given any, there are many morphisms, yes, from C infinity, from either polynomials or C infinity into these dual numbers. Yeah. But I'm saying every one of them is of this form. And in fact, it's not unique because if I put a different value of x, I get a different morphism here.
Of course, so what that means is this, if you consider all possible formalisms from Rx to D, right. Are these the only possible?
Yes. Yeah, they're all of this form, and the only difference is what value I use for x. So if I put x equal to 1, I get one homomorphism, x equal to 0.2, I get another one, etc. And these are all of them.
Okay. Then this will actually be very interesting.
Yeah. Okay, yeah, and last time I gave a proof of it, it was based on the Taylor's series. It's not too hard to do, but I don't want to repeat it now. Yeah.
But wasn't that like, in order for that proof to work, we need to make some assumptions in the first place. Like we need to assume that formula, right?
Assume what?
We need to assume that's a fundamental formula.
Yes, but that's a fact about C infinity. If I take smooth functions, right, a fact about them is that the Taylor's formula holds. So the only assumptions I'm making is that I have the ring of smooth functions and that this map must preserve the algebraic operations. So under those two assumptions, first assumption means I have a Taylor series, then I can just do some computation like I did to show that indeed if it preserves the operations, this is the only thing it could be. Evaluate at a point and evaluate its derivative at that point.
Okay.
Yes.
So there is a smooth function that doesn't agree with its Taylor series though, right?
Well, but remember, this is only Taylor series of first order. To a finite order. I'm not talking about taking a Taylor series all the way to infinity and trying to have it agree there.
But even still, right? Even still, there's this function. It's like e to the minus 1 over x.
Sure.
And then you define it to be 0 at 0.
That's right. And that will, to any finite order, that will agree with its Taylor series up to a remainder.
Oh, I see. Up to the remainder. Okay.
That's right. This is finite order Taylor series with remainder here.
Okay. Thank you.
Yeah, if I took the Taylor series in infinite order, that's not analytic, it would disagree.
I understand, thank you.
I'm only ever doing it to finite order. And in fact, here I'm only going to first order. So the problem is at infinity, but I've only gone to first order, I haven't gone all the way to infinity yet. So yeah, so that's why I do that. All right, so what this suggests is that if I'm going to have my correspondence that's somehow corresponding to these dual numbers, I'm going to have a kind of geometric space which I can think of as an infinitesimally small interval. All right, so what that suggests is, suggests how I can now, how I can make synthetic differential geometry actually a well-defined thing. I'm going to take my category spaces, whatever I work with in differential, to do my ordinary synthetic geometry, and I'm going to augment it with these new infinitesimal spaces. So by the way, so corresponding to D, I'm going to write. So what I'm going to do is, just as a matter of notation, I've used, the boldface D and the boldface R to stand for the rings. And the spaces correspond, I'm going to write in ordinary font. So this I should think of, the space corresponding to this, or functions on it would of course correspond to C infinity of R. If I find what functions are, and then somehow I'm thinking of, I'm introducing this space that artificially, I'm thinking of dual numbers, somehow is wanting to be, real functions on this infinitesimal space. And what I'm going to, now to make that well defined, what I do is I say, well, I have to tell you what kind of a category I'm going to have that has these infinitesimal objects in it. And the way we're going to do that is just as, traditional in synthetic geometry by giving some axioms. So I'm going to give an axiom for a class of categories. And, and we'll start with making room to put the axioms down. So And to write some axioms out. So, and as I mentioned, you know, in synthetic geometry, there's usually many different kinds of axioms depending on exactly what kind of geometry you want. So I'm going to start with a minimal set. And I'll read you a quote about that, but anyhow, so the minimal, make sure here, okay, good, set will be well, I have a category, and this now I get to Noson's comment, so I have a okay, I'll use the letter E since they like it, and I'm just going to say that this category has all limits in it, all right? And now I'm going to start using those limits. So one kind of limit, of course, is a product. And what do products let you do? Well, among other things, they let you talk about structures internal to categories. So I can, for example, in particular, I'm going to want to have a ring object in my category because I'm going to want something that, you know, looks like, say, my ring of real numbers or functions on the real numbers. So, all right. So I'm going to want a ring. So because I have products, I know what it means for an object to be a ring object. I'll be R. So remember, you know, ring object means I have things like, well, I basically, what do I have from, you know, I'm going to have map 0 and 1 from the terminal object into it. So pick out the 0 and 1 element, and then I'm going to have maps plus and times, which go from R cross R, all of which are subject to the usual axioms for a ring. So it's a ring object. Now, one comment here is, since it's internal to a category, you know, we have to be a little bit careful because when we usually do geometry, if we have real numbers, we have it be a field. But when you're internal to a category, problem is to say what a field is, I have to say all elements other than 0 are invertible. And in category theory, internally, there's no good way of really saying that. So all we're going to say is that it's a ring. So we can't quite say that R is a field here yet, although we might be able to say some field-like properties. But for now, it's just a ring object, a special ring object in there. And now, all right, well, that's no big deal. Lots of categories have ring objects. So I'm also going to want to, so now as I've, you know, mentioned these dual numbers, I want to construct, have that. Well, you know, I said all limits, so in addition to products, means I have equalizers. And I can cook this thing up as an equalizer. So let's do it. Right, so given my ring, I have two mappings. One of them is just the mapping that squares an element. And then I also have a map. And I have a mapping that sends all elements to 0. So I take the equalizer.
Because you're modding out, no?
Well, I'm saying them equal. I'm finding those elements. I'm trying to find all x's for which x squared equals 0. So I'm not quotienting it. I'm picking the sub-object of. I'm picking out the sub-object on which these two maps agree. So that's an equalizer. And I'll give this, yeah.
This x squared operation, this is like the diagonal from R to R cross R, then
yeah.
With the multiplication?
Exactly, yeah. That's right. So we can, yeah, exactly. Diagonal to...
He's defining that as Steve.
Oh.
He's defining.
Well, I'm saying, as you know, as Noah just said, right? What I mean by x goes to x squared is, you know, first I can take two copies of the thing and then multiply them.
Yeah, sure, yeah, I got it.
So, yes, I use and another comment I should make is that people who do synthetic differentiality are very much for writing everything in internal language rather than diagrams. So you see a lot of equations like that. In my talk, I'm trying to, translate things. So if anything looks funny, please stop me and I will turn it into a commutative diagram for you. But when I write x to x squared, I just mean, or any x any function, I mean literally it's, using, well, maybe diagonal maps, and these maps, I somehow compose them and I get that morphism.
Maybe a comment is like if you use the category of manifolds, right? Like this will give you nothing interesting. You have to use something more.
That's right. That's right. Yeah, in general, that's right. In the category, and that's in fact the next axiom will be one thing that will make sure this does anything interesting, right? Because you're right. Given any arbitrary category, or let's say category set, yeah. I take R as the usual ring. I get only 0 here. So one thing is I will always have 0 clearly, because 0 squares is 0, but I don't know I have any other infinitesimals. So for that, I'm going to use my next axiom. So sort of number them, which will be a condition. Yeah, so in fact, let me just, so just to be, well, sorry. Just to be complete, I wrote the bottom map, x goes to 0 out. That first you go to terminal object and you pick 0 out. All right, just for completeness. So now the other condition, let me first write it as an equation and then translate it into a diagram. All right, and this is, by the way, known as the Coq-Levert axiom, after the fellow who started it, whose 2 books I'm basing the talk on. All right, so let me write it this way. So first I'll write it in sort of the internal language form, and then remind you what that means. So first of all, this is, I guess, technically an axiom schema because I have one of this condition for every object S in the space, in the category, which I think for every space. So what I'm saying is if I have a map from the space cross this infinitesimal interval into things I'm thinking of as my, numbers, I get another function on that space such that if I take this function of 2 arguments, where the first is in the space, and this is in the infinitesimal thing, it's of this form where I get the function at 0 plus the infinitesimal times this g of x. Now, first comment was, if I took this space S to be R itself, which I could, then this would basically look just like our truncated Taylor series. But I want to ask it not just for that, but for all the spaces that I'm going to work in my category. Yeah.
Here, what is S? Is it any object?
Any object whatsoever. Any object, which then I think is the geometric space, yes.
Okay, so it's like we do have to keep this fundamental equation as an axiom.
That's right.
Okay.
Because here I haven't, see there, here of course I construct things from rings.
Yeah.
But now I'm taking an axiomatic point of view. So if I construct it from rings, I will get this property out.
Even though I think like you could have some weird ring homomorphisms, but sure.
Yeah, well I guess if I use, so let's say, obviously I'll tell you which rings I use, right? Yeah. Not all rings will satisfy this. So if I want to get, a synthetic differential geometry, I obviously can't just put arbitrary rings in. For example, if I pick things like, for example, let's say I picked C infinity, things like polynomial rings, or I pick C infinity, not just of R, but say of arbitrary manifolds, they would all satisfy that property. But of course, I could pick, S would correspond to, I could have, a category of rings where I have a ring S that doesn't satisfy this. And I just wouldn't, then I wouldn't use that.
Okay.
Like, again, if I took my category B set and I, took all rings and sets, this wouldn't generally hold, so.
Like, do these authors make any comments about the limitations of this axiom?
Well, okay. Well, I have a comment I was going to read that might address that.
Okay, great.
So one of the limitations of this is that, well, yeah, I mean, so just to mention, so these are, like I said, well, I should say first limitation, these are just a minimal set of axioms. And these are the minimum you want, because if you just have these, I can proceed, I can, for example, do basic calculus. And in fact, for example, I brought this book along by John Bell, who you may have heard in other contexts. He's written a lot about, type theories and all sorts of topics in category. He wrote a book called Primer of Infinitesimal Analysis. And in fact, what he did in this book was, by the way, it's one of these books where he actually doesn't mention categories until the end. He just talks in the internal language, but he basically shows how using some axioms for synthetic differential geometry, he starts by in the first few chapters, he develops all the things you get in a calculus course. So for example, if you had just these axioms I gave you, you can prove the usual basics like chain rules, product rules, and all that. Yes?
I was just going to say, can you interpret this axiom as like every function has a derivative?
Yeah. Yeah,
E is a derivative of that.
Yeah. It's something along those lines, that's right. That's the way to think of it. So the idea being that, here if I want to have the intended interpretation of my maps as being somehow smooth, having derivatives, I need to, this is a way I can use my infinitesimal to state that. So obviously if you took something like, sets where you had non-smooth maps, this would not hold. So it's a condition on your category. So, like I said, using these, I can just do do my basic things. But then if I want to go beyond basics, one of the limitations, I have to keep adding axioms. So, for example, what kind of things you add? Well, one of them is a simple thing. Let's say in calculus, I know that, for example, if a derivative of a function is 0, that function is constant. But I'm not going to be able to prove that from these things. And because I can, in fact, cook up an example of this where that wouldn't hold. Don't ask me to do it off my top of my head, but somebody's done it. And so then I might have to add an axiom of the form that, for example, if, f, roughly speaking, let me not write it completely rigorously, but, something of the form that if f of x plus epsilon equals f for infinitesimals, then f is constant. Then that means, fx equals f of y for all x. Let's say we're here, f is, say, a real functional ring. So I would have to add that. And then I might want, go further and say, well, what if I want to do integral calculus? I want everybody to have an antiderivative. Well, this tells me that the constant 0 function has an antiderivative as a constant, but doesn't tell me anything else has an antiderivative necessarily. I mean, okay, for polynomials I could get them, but not that, so I would need to add that as a condition. So that is a limitation of this thing, that basically what you wind up doing is in this approach, you just wind up stating known facts of analysis, and then you start using the algebra as a way of accessing those facts. And now I'm going to read you 2 quotes from that, this expository paper of Koch I mentioned, where he says this much better than I could say myself. So the things he said is that, thus full-fledged analysis in axiomatic terms incorporating synthetic differential geometry quickly becomes an overloaded with axioms and is better developed as a descriptive theory describing what happens in specific models. And he says, I prefer not to think of synthetic differential geometry as a monolithic global theory, but as a method to be used locally in the situations where it provides insights and simplification of a notion, construction, or argument. The assumptions or axioms that are needed may be taken from the valuable chest of real analysis. And in particular, that treasure chest happens to contain things like exponential function and trigonometric functions, which we import. And in the context of synthetic differential geometry, it's possible to introduce, say, the existence of these particular transcendental functions axiomatically by functional equations or differential equations. That's essentially what calculus books do. So that maybe says something about limitation. I'm sure it's the limitation you had in mind, but so that the idea is that yes, you in this approach, you just assume I have a category with certain properties. Now, then I can, like I said, I can construct such categories by taking suitable rings. So basically, I want to take rings of, smooth functions of some space or something. I can check they satisfy the properties. But then, once I've done that, the advantage is, given a set of axioms, once I've proven a theorem using synthetic construction with these axioms, I know that will automatically hold for every ring for which the axioms hold. And that can be handy because, again, let's say, the original ring I might have had in mind were real numbers, but maybe the axioms held for some arithmetic ring. Then all of a sudden my whatever differential geometry I could do using those would still be valid over the number field. So that's maybe the way to think about it. Yes, it's limited that, if I'm trying to get all differential geometry, I'm going to be, I could get a mess of axioms, but if I'm just trying to say, okay, what is the most general setting in which a particular result holds, this is a good way of doing it. Given the result, I say, well, what's the minimum number of axioms I need to get that result? And then there's going to be lots of different rings which perhaps satisfy those axioms. All right, so that's the introductory part. By the way, how am I doing for time?
It's 5 to 8.
Okay, well, that's good. So I'll just get to an application of it. So having said this, all right, so, and this won't take too long. So I should, yeah, I'll be done one way or another by 8:30. All right, I'll leave these up for a minute. So the application will be to Lie groups. All right. And let me say why I picked this. Other than that, well, one reason is that actually this is something where an approach involving infinitesimals intuitively makes sense. In fact, that's what Sophus Lie wanted to do when he did Lie groups, but it hadn't been, synthetic differential geometry hadn't been made rigorous then, so he was forced, to do it by other means. And so why is it that I want to think this way? Well, here's it for Lie groups. Well, let's just think of a simple example of a Lie group or a continuous group. Just let's say rotations along one axis, right? So let's say G, what is it, SO2, so that's just rotations around some point, right? Like my clock. So my clock has rotated up to 8 o'clock and it's going to get to 8:30 soon. Right? So there's my group. Now, usually when we're doing, in algebra class, when we do groups, one of the ways we like to describe groups is by giving you generators and relations. And now, of course, and you also, when you do that, you don't want to just, one stupid way of doing that would be to say, well, every element of the group is a generator, and I have all relations this element times that. But then you say, well, that's not really a presentation, that's just giving you the multiplication table. So I somehow want, to pick a minimal set of generators and their relations to describe it. So I actually give you condensed information, not just overload you by telling you what the whole group is. But now let's say we try to study these rotations, using generators. Well, the problem is, what would I pick for a generator? Well, all the elements are rotations through some angle. So I might have a rotation, through, let's say, maybe a rotation, I don't know, through an angle of 1 degree. But then you say, well, wait a minute, I've got, that's actually the half a degree rotation done twice. And and then no matter how far I go, I never get a smallest one. So obviously, trying to make a presentation of this, usual sense wouldn't go very well, because I could say, yeah, I have an infinite series of generators, but then each one is redundantly given by the ones lower down. So that's not so good. So what I would, however, intuitively I say, well, maybe if I could get an infinitesimal rotation, then I could, say, well, this is, infinity over 4 copies of that one, infinity over 2, and somehow I would build it up from that. Now, so where am I going to get an infinitesimal from? Well, I was just saying that in synthetic differential geometry we have infinitesimals. So let's try seeing if we can, if we can define this group as one of our spaces inside, inside our category where synthetic differential geometry works, and then using our infinitesimal object, construct something that acts as its generator. And then to show you that this generator actually does what you would expect a generator of Lie algebra to do. All right? So to get that to work, I'm going to want well, here's the way I'm going to do it. So I'm going to follow the way that, so now I'm going, what I said here, I'm going to follow the way Koch does it in his book, Synthetic Differential Geometry of Manifolds. So there's one way, so what I'm doing now is just going through that. All right, so first thing I'm going to do is to say, well, let's even go with this example. So how would you normally describe, 2x2 rotations? You could describe them as, rotations in the plane, you could describe them as 2x2 orthogonal matrices. So that would mean it's a matrix, 2x2, with the property that M transpose times M's the identity. All right. So what Koch is going to do is say, well, let me assume that I'm have a group, and that group happens to be well, first I'm going to have, and basically inside, I'm going to have the group happens to be living inside an algebra. So, because if I take all matrices, that's an algebra over it. So in this setup, I have my ring object R. So what I mean is internal algebra, meaning it's an object in my category, which is a module over the ring object R. So I'm going to have, oh dear, this is too dark here to write, isn't it?
No, it's fine.
Okay, so I'll just say I have module internal, let me say, module A over this internal ring. Now, I'm also going to want this module to basically satisfy a property like this Koch-Levert axiom I had here. So what I want to do is basically make sure if I take functions that are valued in this thing, so, module over R, so I'm thinking it's sort of an analog of a vector space. So let's say I want to do calculus of vector valued functions. I want to make sure those are differentiable. So I'm going to have to basically assume an analog of this property, which is going to have, where instead of looking at so if I look not just at functions that go from some space into my ring R, I want functions that go into this module. Okay. And then I want them to have the same property that I have this other function which I can basically think of as a derivative of that. So I want to be able to take, so the idea is intuitively I want to be able to take derivatives of functions that are valued in this thing. Just like here, I would, if I was taking, let's say, a one-parameter family of rotations, that would mean I'd have a function from, say, a real interval into this vector space of 2x2 matrices. So I want that to happen. Okay, so it's internal module. Yeah.
A is supposed to be the algebra.
It's going to be yes.
Yeah, okay.
It's a module, but it also comes with a multiplication. I just haven't said that yet.
Eventually you'll talk. Yeah.
Well, I'm about to say. In fact, I've just said it now. So.
I was like confused when I was writing it algebra. Okay,
yeah, Well, yeah, because before I got to the algebra, I had to point out it had to have this. I didn't want any old module. I wanted one where I could basically differentiate functions from a space into that module. So I can do my calculus using that as a target. And now, yes, I also want to be an algebra. And so now I can say, suppose I have a group G that sits inside the multiplicative monoid of that. So is subobject of monoid of A. And again, this, you can think of this classical example. You know, here's my 2 by 2 matrix. There's some kind of, you know, vectors. They're a module over R. They're an algebra over R. And the group is given by this subobject, the ones that satisfy this condition. They're transpose times the transpose is the inverse. All right. So I've got this. Now, what I can do? Well, so as I said, I can, you know, if I have my, let's say, continuous group, I can think of, you know, families of it, like a one-parameter family of translations or rotations, let's say. So, for example, I might have something like, you know, right, where inside, where I could interpret SO2, you know, as if I have a category like this, I have, well, I just construct this. And now, by the way, one comment is that if A is a finite-dimensional module of R, so it's just n copies of R, this fact will automatically follow from the fact that it happens for R. Because I'm just saying I have a function into n copies of R, so I just do one copy at a time. However, we can have more general situations. And I'll say what some of those are in a minute. But way more general things than that, like infinite dimensional stuff, which is, but let me not, you know, let me not get too far ahead of myself, so just stick to this. So everything on now you can think of as just rotations for a purpose of understanding what's going on. So then the idea is that, like I said, imagine I take something like a curve of these. Now, what I can do is I can, you know, I can, in the usual way, let me restrict to my infinitesimals. So if I'm given a curve, I can imagine, well, I have a point here, and I could sort of, you know, loosely speaking, imagine what it means by mapping D into R to say I have a point that's infinitesimally close to it. All right? And in fact, there's a bit of notation that we can sort of imagine if I fix a point on that, fix a point in space. And let's say, well, say first I fix a curve. I can pick, you know, this infinitesimal neighborhood. I have a relation that the 2 points are infinitesimally close, that they differ by something in D. And now if I have a space, I can think about points in the space being infinitesimally close if I can say there's a curve that passes through them, and on that curve they're infinitesimally close. So I basically map from D into that space. All right. So what I'm going to, so I'm being a bit loose here, one can, you know, just for sort of time, but at any rate, so let me first look at, restrict my attention to points of the group that are infinitesimally close to the identity element. So remember, my group is, you know, sits inside the algebra, so that means things in the algebra that are infinitesimally close to the identity. All right? And I can prove some very simple facts. So first of all, a bit of notation. They write this to mean that the points A and B are infinitesimally close, which just means that, you know, let's say if there are things on a real line on my R, that means their difference lies in D, or if it's inside a thing, it's an image of something which lies there. All right. So first fact I can show is that, let's say inside my algebra A, suppose I have any element, okay, yeah, right. Okay, so let me, all right, now I'm going to replace axioms with theorems. So we're going to write, I'm going to write down some theorems from Cox. So first theorem is that, suppose I have an element of my algebra that's infinitesimally close to 0. All right? Then I want to check, and I have any other, so in fact I have two elements in my, let me say A and B. Okay, so A is infinitesimally close to 0. Now, then, is also infinitesimally close to 0. And the reason for that is, well, being infinitesimally close to 0 meant basically it was proportional to my thing which squared to 0. And so when I have two A's here, that'll square to you know, the square 0 infinitesimal, so I get that that thing is so close to 0. All right? So that's the first basic fact. Now, what am I going to do with that fact? All right? So next I'm going to know, well, all right, next I'm going to notice that if I take the elements that are infinitesimally close to 0, they form a group. Or rather, well, so if A goes to 0, I'm going to do the following. I'm going to note that, well, if I take, as a consequence of this, 1 plus A minus A, you know, I multiply it out, well, when I'm going to get a 1 plus A minus A minus A squared, but that went to 0. So there, yeah. Right, so that means that basically 1 minus A acts as an inverse to 1 minus A. All right, so these act like that. Now furthermore, I'm going to actually notice, then I can take this thing a step further. So these elements of the form 1 plus something infinitesimally close to 0 form a subgroup. All right? Now, then I'm going to notice that, let me take a commutator of two such things. First, well, that's, as we said, these are, oh, sorry, 1 plus B inverse. So I'm taking a commutator of these two things. As we said, the inverse of 1 plus A is 1 minus A. Inverse of 1 plus B is 1 minus B. Now, I multiply this out, I get lots of stuff, but the thing is that anything where something appears twice is going to go to 0. So, you know, terms cancel.
You mean anything where A appears twice?
What?
Anything where A appears twice?
Yeah, or B appears twice, right?
B also?
Because here I'm assuming both A, sorry, so up in this case, I'm taking the commutator of two things, both of which are close to 0.
Okay, I see.
See, in here, I only assumed A was close to 0, and I let B be wherever it wanted to be.
Yeah, I got it. Yeah.
But if both A and B are 0, now I'm taking a commutator. So all that's going to be left is, well, you can write it like this, or in other words, 1 plus the BA, because the A squared was 0, anyway, so that's all that's left. So I have my, so what happens, I have a group, these elements form a group, and the commutator of them winds up, you know, being this kind of bracket thing that looks like the Lie bracket. It's a commutator in my algebra. And I guess the other comment to be made is that you can check, of course, if 1 plus, you know, I had this, so far I said this was an element of the algebra. But remember, my group was, you know, let's say if it happens to lie in this G, which is a sub-object to the algebra, I can easily check if 1 plus A in there, 1 minus A will also have to be in there, because it's the inverse of it. So, in fact, so basically this gives me a way of very literally saying, you know, what is my Lie algebra group? I just take all the elements that are in infinitesimal neighborhood of the identity, and they form a group. And the operation on that happens to be the Lie bracket. So I literally get my Lie algebra, because ordinarily you might, in Lie theory, you'd say, well, it's a manifold, I take the tangent space, and somehow I get a Lie group around it. Well, here I get it quite literally with this infinitesimal interpretation. And I can then go further. So in what sense, and furthermore, what sense can I say that they generate a finite transform? Well, suppose I have, again, my curve in there. So loosely speaking, I can imagine, that, well, given every point, I can take an infinitesimal neighborhood point, and each one, it's one of these generators, so they all they multiply to get a curve. Or a better way of saying that would be, I could write, given a curve, let's say a map from here to here. So let me give this map a name, F, right? Well, I can write the equation for it. I can say that I'm going to do, let's say, F inverse of X times equals, let me define it this way. So I take F inverse times its derivative. That's going to be, so what does the F inverse do? It takes, so it's, again, we can interpret this with the infinitesimal here. So we can think of this as, of X times, well, F of X minus X plus epsilon. All right, and then, of course, in other words, well, that's 1 plus minus, okay. Well, so that's our G of X. So basically, again, this is going to be one of these things, in the infinitesimal neighborhood identity. So given a one-parameter family of these, I can say, well, the derivative of this thing is determined by that. And again, to say that, this goes back to a comment I made earlier where you might have to make an extra assumption to say that your differential equation has a unique solution. But we can do that in synthetic differential geometry. So in that sense, I have this differential equation, and the G of t here, if I interpret as an infinitesimal, is one of these things infinitesimally close to the identity. So in that sense, I can say, the Lie algebra generates the group. That these are generators, and they have, and they're going to have commutation relations of Lie algebra for their relations. So in that sense, I can say, yes, if I have this kind of setup here of a group sitting inside one of these spaces, there's a certain sense in which I can say it is generated by infinitesimals whose relations are commutation relations of a Lie algebra. All right. And I can take this game further, because here I used a square zero infinitesimal, but I could say, well, what if I went to higher orders? Let's say infinitesimal was third order, for now third order was 0. Then I have infinitesimal squared. And for example, by doing more playing this game further, for example, I can then show that, yes, this bracket really does satisfy the Jacobi identity. And then I can also show that, I pick some order, let's say 10th order or whatever. Then I can show that, well, if I know the commutation relations, I can, figure out what's going on to all orders. So I get analogs, some analogs perhaps weaker, of the usual things I would expect of the way a Lie group is determined by its Lie algebra. Now, in classical geometry, I would say, the group, there's the algebra actually determines a group in some neighborhood of the identity, but here we don't necessarily have a notion of neighborhood, but we can at least say, well, to, any order. So that's sort of a, proxy for neighborhood, so you can at least, so you get some of that. Now, let me finally mention what got me onto this topic in the first place. The fact that, so, what I mentioned now was something, was just taking old stuff, like rotation groups on a plane and just saying, well, this gives you an more intuitive way of thinking about it, where you can actually literally say I have generators in this interpretation. But it turns out you can actually go well beyond just stupid rotations in the plane to infinite dimensional groups. You see, so first let me make an extra assumption now that my category is Cartesian closed. So that means given any two objects, I have the exponential. In other words, an object of mappings between them. So, for instance, and let me just think where I want to go. Okay. Yeah. By the way, how am I doing for time?
15 more minutes.
Perfect. That's all I need. So, good. I've gotten the punchline, so. So, for example, I could also imagine, well, let me just, so like I said, let's say I have mappings from A to B. So, for example, suppose that A is a group, right? I almost mentioned this a little bit earlier. So let's say I have a group to any object, let's say the real line, right? So I can obviously have, this is a group itself because I just, to multiply at a value of x, I just take, well, 1 of x times g2 of x. So all the mappings from, really any space into my group, so let's say R, any old space in a group form a group, under pointwise multiplication. However, this thing is, however, let's say, typically you'd say, well, if let's say this group was even just a rotation group, some Lie group like our SO2, and this space was, well, let's say a line, well, that's already mapping functions from a line into, into the main group are an infinite dimensional function space. So I've got here a group which is infinite dimensional, So ordinarily, Lie groups are usually, you read most books on them, they only define them for manifolds. Or then maybe you get some extension beyond manifolds. But the nice thing is with synthetic differential geometry, you actually can take the same thing I told you here and at one fell swoop, get all these infinite dimensional things in there as well. And so I had to do some proving. Now for that to work, remember there was one caveat, that namely that this algebra as a module over RR had to satisfy the condition that allowed me to differentiate. So one of the things I did a bit of homework. So it started with when I was reading an intriguing comment. First, it was an intriguing comment by Koch. So in his book, he's just mostly interested in just ordinary Lie groups, the ones that are manifolds. But he makes the intriguing comment that with this thing, if you take, he makes a comment that if you take R to any object, it will have this property. So that gave me some hope, because this could be infinite dimensional. And so I checked, and like I said, I did some homework, and I'm not claiming the results are new to me. I'm just going to call them homework, basically trying to check if this would apply for my case. So I asked, okay, so as I said, how can I get, if I take a finite dimensional module over R, I know it has this property. What other ways are there? What are some other ways of constructing modules that satisfy this property? And I found out there's actually, well, I'll just write down the results I had. So one of them is, well, this patient 3. Oh, wait a minute. Oh, lemma 1, here it is. Okay, so first, let's say, so let me say V and W are, so I'm just going to call them, so Koch-Levert modules, by which I mean this Koch-Levert property holds for them. So I notice if V and W have this property, well, first it's not so hard to show. You just basically draw a commutative diagram that I take the direct sum of two of them, it'll have this property. That's not a big deal. Just write down, chase a little diagram. Okay, but then it gets more interesting because if I take, all right, V2 maps from any space into V, they'll sell this property. That's the thing I found that was left as an intriguing exercise in Koch, so I did the exercise. But then I took it further. Oh, lemma 3, I also noticed that, furthermore, if I take any equalizer of them, it'll still have this property. So now if I start with some module, let's say the one module we know that works is just R itself. Well, clearly by taking products with itself, I get R to the n. Then I can take it to powers. Taking equalizers, I can generate a heck of a lot of different modules. And most of a lot of things that would, naturally come up in the course of, using these three operations, you'd probably build up a lot of modules, and certainly all the ones I needed for a certain practical application I had. And then, next I can ask, well, what about groups that sit inside, inside these modules? What can I say about, what groups there are? Beyond just the ordinary finite-dimensional Lie group, which clearly would work. And so then next I did chase some more diagrams, and here are the results I found. So first let me, sorry, take me home, my notes. Here we are. Okay, that's the, that equalizer thing is, by the way, two pages of chasing diagrams. All right, so I won't even try to write them down. But, so what I found was, all right, so let me say with groups, so now, or I'm going to call them again, okay, groups, so that just mean that groups that if I take, a module, which I endow with an algebra structure, and that group happens to be a subgroup of it, what kind of groups can I generate that way to which this version of Lie theory will apply? And so what I found out was, okay, let's see, yes, so then, okay, well, there was the coordinate stuff, all right, here we are, so let me just get to those. Well, a couple of things I did, but okay, so I called them, so I found out, here we go, you see, sorry, Cartesian, okay, so again, one thing is, I take the product of groups, it'll still have that property, so I can handle it. Next will be, if I take any object whatsoever, G to the S is that, so the example I mentioned earlier, they work. And then finally, I also checked that, okay, in fact, let me just put this down, yeah. The hard one to prove, let me just get it straight, Cartesian product, sorry. No, we put that, yes, yeah, that's right. In fact, semi-direct products, all semi-direct products will also have this property, and that's the hard one to prove. And the nice things again, and remember I can iterate these operations. So for example, I could do things like I take the G to the space, like semi-direct product, that gives me so-called wreath products, and I can make towers of these things, products, and basically by that I can come out with all kinds of things like, for example, diffeomorphism group of some space or something constructed from that. And that was actually something I needed for something, believe it or not, for a project I was doing in theoretical biology. Because to solve a certain model, it turned out solving that model wound up involving the action of some infinite dimensional group. And I wanted to treat that as a Lie group. And that's what led me to look at synthetic differential geometry. Now, so just to say the crazy path that led me to this topic.
Great. Any questions?
You didn't discuss any of the things I was expecting.
Oh, well, what were those? Well, you didn't give me a list ahead of time, so how was...
I was sorry, you're right. What about all this weird internal language and its relationship with the meaning of the word not? That's what I was expecting.
Oh, the word not, well, okay, we've already took that before, right?
I know.
I mean, what would you, how would you, you're into, as you know, in category theory of intuitionistic logic, so all we get is a pseudo not.
Yes, that's what, yeah. That's what.
That is a quick answer to that question. Yes.
What do we mean by that?
Well, if I take a, well, all I mean is if you take a statement where you have the ordinary negation,
Yeah.
I can't that doesn't, in classical logic, I have an ordinary not, which has a property that double, not A is A.
Yeah.
The closest thing I have in intuitionistic logic is a thing where not A is the same as not A, but not A is different from A.
You know that, right? So it's not Boolean logic, it's
Yeah.
intuitionistic logic.
Yeah, it's a weaker form of logic. Yeah, sorry.
I have one small question.
We'll explain later.
Yeah, we know that for certain spheres, we could view the spheres as a Lie group, right?
Sure.
And so technically speaking, we could establish this synthetic differential geometry theory on some spheres.
Sure.
And then, now, as we mentioned, if for object A, that A satisfies this property, and the map from A to another space B would also satisfy this property, then there is a surprising potential application for this theory that you could potentially establish these synthetic differential geometry theories for some homotopy groups of other spaces.
Okay, well, homotopy, then you have to, well, see, but homotopy, I have to have a homotopy relation in here, right? I'd have to throw in homotopy.
Yes.
No, I mean, because
Yes.
by definition, what is higher end of n? It's literally all the class of all mass from the sphere.
Well, but modulo homotopy.
Okay.
See, here I'm just doing ordinary one category, so I don't have the notion of homotopy. Now, if you were to do this in an n category where I have a notion of homotopy, then I could do that. So far, I've just been doing ordinary one category or one topos. So to get homotopy, I'd have to, either put a model category or an n category or something like that in, I'd say, which I haven't done here.
I was just going to say, if I understand the question correctly, right? This sort of gets to, I mean, there's a notion similar to that, which is the Goodwillie calculus, and we're in this group read on the thing that sort of.
Well, that too, yeah.
Julian's exactly a
Right.
Goodwillie calculus, and it's not about differentiation in this sense, but it's about
Yeah.
the homotopy operations as having a differential quality
Right.
in terms of how they act on polynomials.
Yeah, or maybe, for instance, or at least this is a surprising application would be that it could shed some light on the spherical mapping of the
Well, I mean, well, there's one thing. One, you could certainly formulate them this way. Now, whether this tool actually helps you prove any theorems that, a topologist is another story.
Oh, I mean, yeah, so
Right, the hard part is actually do something with it. Yes, one can certainly formulate it this way. Now, whether that gives you an insight into it, is another question.
Right, that's true. I just wonder, like, if theoretically we could establish this, for those spherical maps,
Yeah.
then, if we actually do it, does it give us anything new, or it would be trivial?
I don't know. Yeah, I don't know about that, so I have no idea. I mean, now, like what Gersha mentioned is, partially in that direction, because yes, there is Goodwillie calculus, which topologists study that can be formulated in a similar way to this. Not exactly that, but at least uses some of the ideas from here, so. Yep.
Yes, this is kind of a not well-defined question.
That's okay.
But I'm just thinking, like, it seems like there's a sense in which any group object in one of these categories can be thought of as a Lie group. Am I right about that? Like, if you have a group object in one of these categories, then you cook up an algebra by looking at the mapping object to the real number object. This is the algebra functions on this.
Yeah, but then it may not. But then you may not necessarily satisfy this property. It might not satisfy that property, that algebra. You could write.
I thought it did because of what you said over here.
Those are KL groups. See, he says take.
If the group already satisfies this, then if I take a map from a group that already is known to satisfy it, not an arbitrary group. That's the. See, this is given groups that already satisfy that. I can combine them, make bigger groups, but I can't. But I have to start with something which I know this works for. So not saying arbitrary. Yeah.
If you think of a Lie group as a group object in the category of manifolds,
Yeah.
then this is not in generally a category of manifolds. It's not always just that pretty.
Well, yeah. Right, but I mean, I guess I could have, well, for example, I could have a group object there. Imagine the group object, let's say even just, imagine something like, something that wasn't a continuous looking group at all, like some fractal or some crazy group like that. That wouldn't, it could be some big, crazy discrete group or something like that too, I might have in there.
So just to be clear, this applies if you have an internal algebra, and then if you have an algebra that satisfies this condition, then it's a group of units.
Yeah, or a subgroup of the group of units, yes.
No, think of
I mean,
groups of matrix algebras.
Yeah.
Right, like the SONs.
Well, a subgroup of an algebra has to be by definition a subgroup of the units of the algebra, because group elements are all invertible. Yeah. So I can take. So point is, if I take any algebra that happens to have this nice property, the subgroup of units of it behaves like a Lie group. And then on any subgroup of it and other groups I construct from it will still behave like Lie groups.
That's a nice way to say it.
That's maybe the better way of saying it. So I need the starting point I need the special type of algebra, and because otherwise I might have, given any group, yes, I construct an algebra, by taking linear combinations of it or whatever, but if the group was some kind of, crazy discrete group or something, I wouldn't expect that to behave like a Lie group. So I could have, groups inside my category, internal groups of category, which, I could find an algebra, but then the algebra wouldn't have this nice property of, I could differentiate with functions into it.
Yeah, intuitively, you shouldn't expect the algebra functions on any group to be able to afford you calculus.
Yeah, exactly.
Well, if you pick any original group and then say, I'm going to look at all the functions on that group to the real numbers.
Right.
You shouldn't expect to be able to differentiate those functions in general.
Right.
Sure.
That's what you're saying.
That's exactly my point, and that's why and that's the condition. Yeah, exactly.
Sorry.
Right.
No. You want to say something, beautiful? Okay, I'm restraining myself. I'll wait for dinner, but I will say one thing. There's another approach to infinitesimals, Abraham Robbins.
Yep.
And that, of course, at least naively, this is very stupid and trivial what I'm saying, but it's true. Any infinite set comes with infinitesimals in his setup. Finite sets,
kind of ideal elements.
but infinite sets always have adherent infinitesimals and infinite elements. Always, period.
Yeah,
So,
sure.
if you're worried that your thing is discrete, even if it's as long as it's infinite, that's it. You're off and running.
Sure.
It's trivial.
Okay, so let's thank the speaker.
Yes. However, just to mention, those are infinitesimals come by doing model theory, and they may not have any properties that look like that you can do derivatives with them.
Three different properties.
So they may.
Right,
So you've added infinitesimal elements, but there's no guarantee that you can. Yeah.
So what does this say beyond this, the beyond part of any model? Any theory?
So these things will just basically be algebraic.
Yes.
So you can think of it. So you can think of R.
Well, inside of nice algebras.
Inside of nice algebras, but algebras include things like.
Oh boy. Oh wait.
Like,
no, that's not it.
Finite,
Where did that?
finitely many.
It's in your